Welcome to the pre-class video assignment for section 3.3. So we're going to look at now something called Laplace transforms, and ultimately we're going to see how to use Laplace transforms to solve initial value problems, basically. So there's a bit of explanation. In this section, we are really just introducing what the Laplace transform is and how to compute them. And we will be working on solving DEs and initial value problems a little later. But for now, let's take a look at the idea here. So just as a motivator here, in calculus, we have previously talked about the derivative operator. We probably in Calc 1 saw it as ddx. We've used it in this course as just capital D, right? So these are letters. They do not represent a quantity. They're not variables. They represent an operation. So they're an instruction to do something. In this case, they're an instruction to take a derivative. So we, again, are familiar with the derivative operator. You can think of the derivative operator as a transformation. So that is actually the sense in which we're using the term Laplace transform. So we have a derivative operator. So this is a transformation of a function t, namely into its derivative. And then this derivative operator, or this, derivative transform has some properties. Things like the linearity property. Again, we know this as you can take derivatives term by term and just move the constants in front, right? So the derivative operator acting on C1 f of t plus C2 g of t is C1 d acting on f plus C2 d acting on g, i.e. C1 f prime plus C2 g prime. This is linearity. Yes, you can do the operator term by term, moving the constants out in front. Another property that we have is a sort of inverse. That is, we can reverse the process or reverse the transformation of the derivative operator. And of course, we know this as integration. So we have an operation of integration. If we ignore the plus c, the operation of integration is the inverse operation of d. So again, this is all just analogous. We are going to introduce in this section something called a Laplace transform, and a Laplace transform is also an operation. It takes a function and transforms it into another function. The difference here is the Laplace transform is actually an integral transform, and basically, we are going to see how we can use Laplace transforms in order to solve initial value problems. All right, so a Laplace transform has properties such as linearity and has an inverse, as we shall see a little bit later. So that's kind of why I wanted to talk through this idea of a derivative operator. This should seem very familiar. And a Laplace transform is just a different type of operator. So it is an integral operator of sorts. It is actually based on a Laplace transform, basically is an improper integral. So this is something we should remember from Calc 2, an improper integral. So in Calc 2, there are actually a few different types of improper integral. The one we are interested in here is this kind here, where we have an infinite interval of integration here. This is the type of improper integral that we actually need for this section. So let's take a little look at that a bit more closely. Here's a review a little bit improper integrals. So again, Laplace transforms are a type of operator that involve taking an improper integral. Again, the type of improper integral is sometimes called a type 1 improper integral, and this is where you have an infinite interval of integration. So how do we evaluate an integral such as this? And again, that's what we're going to review real quick. So note that the integral from a to infinity of f of x still can be thought of as an area. It can be an area under the graph from A all the way to infinity. The somewhat counterintuitive idea is that even though the region might extend off to infinity in the positive x direction, the area itself does not have to be infinite. In fact, it doesn't even have to be very big. So that is sort of the counterintuitive idea that we have for these improper integrals. So how to work them? So you will have seen this in Calc 2, so just a reminder. The idea here is we first turn our improper integral into a definite integral using some other letter up here. Here I used T. I think in the notes I might have used B. The letter name here is not important, but I basically turn this into a normal proper integral with a variable T. You basically evaluate this integral and then take a limit as T goes to infinity. Notice that when you evaluate something like this, assuming that A is a known number, what would happen when you evaluate an integral like this? You find an antiderivative for F, and then you would plug in the T minus plug in the A, a fundamental theorem of calculus. If A is a number and T is a variable, it means what you end up with is a function of T. And then we take the limit as T goes to infinity and evaluate that limit. So it's really a two-step process. We do a definite integral to get a function of T, and then take a limit as T goes to infinity. This is the method. So that's basically what we're looking at here. Now, the results of an improper integral can be one of two things. We either consider them as convergent or divergent. If the limit you end up with is a finite number, if this ends up being a finite number, then the improper integral converges. Otherwise, we say that it diverges. So that is basically the idea. It is worthwhile keeping in mind under what conditions will one of these things converge. So basically the idea is we're going to have an integral that looks something like this, right? We have some starting point at A, and we can imagine having some graph, something graph like this. So the integral that we're talking about is an area underneath the graph that goes off to infinity like this. So for this region to be a finite area, what it requires is that we certainly have to have we would certainly definitely need to have a graph that is asymptotic with the x-axis. If instead we had a graph that did something like this, and you're adding up this sort of area, clearly this is never going to be finite if the accumulating area is increasing. So that is never going to be convergent. So we certainly need a graph that comes down to the x-axis and is asymptotic with the x-axis. But that is simple. That is by itself is not enough. It also needs to come down fast. It needs to come down quickly enough to be sort of convergent and not be adding on, accumulating too much area over here in the tail area. So that's kind of the idea. We can look at a couple of basic examples. You can try these out for yourselves. But it turns out that if you do this guy here, the improper integral from A to infinity of 1 over x is certainly asymptotic with the x-axis and decreases from some point onwards, but it doesn't do so fast enough. This still diverges. If, on the other hand, you look at this improper integral, the integral from A to infinity 1 over x squared, this is also asymptotic and kind of looks similar, but this one comes down faster than this one, and hence this one actually does come down fast enough and indeed converges. So you can try these out and see that this is the case. So that's kind of what something useful to keep in mind. An improper integral will converge if we are basically adding together a region that is coming down fast enough. If it doesn't come down fast enough, then it will not converge. All right, so let's take a look at a couple of examples. On the note packet here, we have a couple of examples. Evaluate the following improper integrals. So here is just a Calc 2 improper integral. This is not a Laplace transform per se, but let's just see how this works. So the first thing we have to do is set this up as a limit, and it should always be set up as a limit. There is a tendency for students to want to forget about the limit itself, or at least in their work, they don't write limit, but this needs to be written as a limit. So I set this up as a definite integral from 0 to b, and then a limit as b goes to infinity. So you would have to evaluate this definite integral by parts. So this is a by part situation. So I did that over here in green. I did the by parts and I set it up over here. And then I can evaluate, this is the first step of by parts. This can then be integrated. And basically I get this function here. And I can evaluate it as a definite integral, fundamental theorem of calculus, put the b in first, and then put the 0 in like this. So then, again, all along here, we are now going to consider taking the limit as b goes to infinity. That is an infinity. That looks weird. That is an infinity. B goes to infinity here. So notice negative b over 2 is just a constant. We've got an e to the minus 2b. E to the minus 2b is, of course, 1 over e 2b. Yes, it is 1 over. So if b goes to infinity, 1 over e to the 2b is going to 0. So this is going to 0. This is going to 0. For the same reason. So this goes to 0, and we're just left with minus -4. So we get the finite result of 1/4. Since this is a finite number, this one converges. All right, so give one a go here on my open math. All right, here's another quick example. Again, similar idea. Here is a improper integral, not necessarily a Laplace transform per se, but this we can set up this improper integral in the same way. We make a definite integral out of it, going from 0 to b, and then take a limit as b goes to infinity. Then we integrate. So 1 over x plus 1 is ln of x plus 1. We evaluate this by the fundamental theorem of calculus, put the b in first, minus put the 0 in. Of course, ln of 1 equals 0, so this goes away, and we just have the limit as b goes to infinity, ln of b plus 1. So we should know our ln graph. Ln graph does something like this and goes to infinity slowly, but it does go to infinity as b goes to infinity. So this goes to infinity. Since this is not a finite result, this is a divergent improper integral. So give one of those a go on my open math as well. All right, so let's take a look at the definition of the actual Laplace transform. So suppose a function, suppose a function f of t is defined for t greater than 0. So we're really only ever looking at t greater than 0 here. The Laplace transform of f of t is defined to be the following function. So there's a couple of notations here. I'm using capital L of f of t. This is my operator. It says take the Laplace transform of f of t. Another notation here is the Laplace transform of little f of t is big F of s. So notice here that the Laplace transform of a function f of t has a whole new independent variable s. That is usually the letter used here. And again, this is an integral of sorts, so we're kind of using this little f, big F idea. You would have seen that early on in calculus as a way to notate an integral. This is not a literal integral, it is, but this is the notation used. Just a quick note here, a lot of books use a sort of fancier script L type thing for Laplace transform. I do not have one of those in my math palette, so I'm using just a capital L in our notes. So the Laplace transform of a function little f is, so this little symbol here you read that as being defined to be. So the Laplace transform of f of t is f of big F of s. It is defined to be this improper integral. So it is the improper integral where you stick in an e to the minus st times the function you're finding the Laplace transform of, and evaluate this improper integral. So this is what it's defined to be. Again, notes here, the Laplace transform is a function of a whole new variable, s. It's not a function of the same independent variable that you started with. If the improper integral defined here converges, then the Laplace transform will exist. Notice that in general, this is kind of a good thinking idea here. The Laplace transform really ought to exist for most functions because of us throwing in this e to the minus st inside our improper integral. So realize that, again, what criteria, when does an improper integral exist? Well, it exists if the function you are integrating goes down quickly. So for most functions, if you basically divide by e to the st, as far as elementary functions go, we are dividing by a function that gets bigger faster than just about any other elementary function. So if f of t is any other elementary function, e to the st still gets bigger faster than that. And the overall effect is that you get an improper integral that really ought to converge for virtually all for most functions. So that is kind of the clever idea here. Throwing this guy in here is kind of forcing this integral, forcing this improper integral to converge. All right, so let's try a couple of them here. First one here is the simplest one of all. What is the Laplace transform of the constant function f of t equals c? So Laplace transform of c. The definition says we set this up by throwing in an e to the minus st inside our improper integral times c dt. So we just need to evaluate this. This is fairly easy in terms of doing this. We can set up our improper integral from 0 to b, take the limit as b goes to infinity. The c will just sit there. And again, we just need to find the antiderivative of this. So notice we've thrown in this e to the minus st, but the t is now considered the variable here. We are integrating with respect to t and treating s as a constant. That means when we are done, the t is going to be replaced by 0 and b, and we will be left with a function of s, as we have stated previously. All right, so integrating this with respect to t would give us there's be a c just sits there, but we would have a 1 over s, negative 1 over s, e to the minus st. And again, you can always check this by differentiating. Then we plug in, and again, notice that, again, we're usually a bit lazy, but it might be actually helpful here to say that we're really doing the integral from t equals 0 to t equals b. If you put the b in first, according to the fundamental theorem of calculus, we would get this guy, right? We're putting the b in for the t only. We get this. And if you put the 0 in here, you get e to the 0 is 1. So we just get c over s. And then notice if we take the limit as b goes to infinity, this e to the minus sb is like having 1 over e to the something times b. This is going to 0. So this term goes to 0, and we're just left with c over s. So that is basically it. The Laplace transform of a constant c is the function c over s. But this is the function here. Again, so that's a fairly easy one. Here's another example. What about the Laplace transform of f of t equals t squared? Again, the setup is fairly easy. Laplace transform of t squared is setting up this improper integral, t squared, and an e to the minus t thrown in there. Then you can set up the improper integral, and this one then is something we need to integrate, and this is something we can integrate by parts. So I've actually put this in here as a MyOpen Math question. So I'm going to have you do something like this for a MyOpen Math question. This integral, so be able to carry out an integral like this. It is a by parts, so give that a go here. So without too much further ado, if you work this through, or you can again pause the video and follow the notes here. But basically, this is where it got me. I needed to do biparts twice. It got me down to here. Then I plug in the b's, plug in the zeros. The stuff with the b in it is all got an e to the minus sb in it. This is all going to go to 0. The stuff that we put the 0 in is really just ending up being this guy. So I have a minus 2 over s cubed. So this is our result. The Laplace transform of t squared is 2 over s cubed. Some of the questions we'll ask about domain. The domain ends up not being a big deal to us here. As it ends up not being something we overly have to worry about, but just to answer the questions in the note, in my open math, notice the following. We're throwing this guy in here, and for this thing to converge, I really need that e to the minus sb is basically 1 over e to the sb. So I need this to be an actual negative here, so that this ends up in the denominator. So the domain requirement for this to be true is that I need the s to be positive, because if s were negative, we would have a double negative here, and this limit would not go to 0. So we actually have a similar situation here. I'm going to need the s to be strictly positive in order for this to go to, for these limits I'm claiming to actually be true. All right, so here's a similar little question for to actually do a Laplace transform. So I think this one is something like f of t equals at or something like this, something times t. So give that one a go. And then the last one here in your notes is the Laplace transform of cosine at. This one is a bit of work, but mainly because of the integral we run into. Notice that, okay, setting this up is not too difficult. What is the Laplace transform of cosine of at? It is, again, this by definition, the improper integral e to the minus st cosine at dt. So to continue, we need to be able to integrate something like this. And this turns out to be a bipart. So this is an integral you should have seen in Calc 2. It's kind of a tricky, weird one. It requires doing biparts twice. So here's a little my open math question to do an example like that. Again, it is scaffolded, so it's going to step you through the problem. So give that a go. All right, so you should be satisfied then that integrating, and again, there's a bit of work to get from here to here, but integrating this guy here gives us something that looks like this. And again, we can then put in our b for t and then put in our 0. So when we do that, we get in something that looks like this, but this has an e to the sb in it. As long as s is positive, this whole thing will go to 0. So that goes away, and then the only thing left is a negative minus s over s squared plus a squared. So this is the Laplace transform of cosine of at. Again, so that was a bit of work. Some good news is, while you should be able to find some Laplace transforms, we are going to ultimately approach this in a different way. So we will not be having to do a bunch of these, except I'm going to probably ask you to do some on a test. But we should be able to do this sort of thing. All right, so a couple of little examples to try still. So give that first one a go, then give a second one a go. And that should be it. We will complete the rest of this packet together in class. Thank you.